So question number 1, a projectile is fired at a speed 100 meter per second at an angle 37 degree above horizontal. At the highest point it breaks into two parts of ratio 1:3. Smaller one stops momentarily. That means when it breaks into two parts, the smaller one stops and drops onto ground. Find the distance where the heavier piece lands. So if we draw the diagram here, from ground the projectile is launched. So we will later on put the values with velocity u and making angle theta with the ground. So here it goes, and at the highest point it breaks up into two parts of mass ratio 1:3. So this was traveling with a speed u cos theta. Okay, so let the mass be 3m. So let 3m be mass of the particle. So when it breaks up, so before the breaking up, so this is 3m moving with a velocity u cos theta, and after collision m happens to be at rest while 3m moves, suppose it moves at velocity v0. So we have to find this v0 first. Okay, so you can conserve momentum. So 3m multiplied by u cos theta is equal to m multiplied by u plus 1:3. So if it is 1:3, so it's actually not 3m, 4m, right? We should have taken it 4m. Let 4m be mass. So 4m. So this will be 4m into u cos theta equal to m into 0 plus 3m into v0, implies v0 is equal to 4 by 3 times u cos theta. So after collision, this, so m, this drops here, m, while this 3m moves with a velocity. So 3m moves with a velocity v0 which is greater than u cos theta, 4/3 u cos theta. So it will drop here. If would not have been broken, then it would have traveled here. Right now it is having more velocity, so it will drop certain distance beyond. So actually if it would not have been broken, this is the path of the center of mass of the system, right? If not broken, then this is, so as during splitting up, it is all the internal forces that are involved, right? So the center of mass would have dropped here now, which is equal to range. So what is the range? U square by g times sine 2 theta. Now there, suppose name it as r. You can write it as r for the range. Later on you can substitute range. So this is r by 2. Now what about this distance? Let the distance be x. This is for, this is path of mass, this is path of the mass m, this is path of the center of mass, while this is path of the mass 3m, right? So 3m, so 3m mass drops here while m mass has dropped here. So we can apply the formula of center of mass, right? So coordinate of center of mass, so total mass. So what is xcm equal to? So xcm equal to r. Now this is the 0 for us and this is the x coordinate. So xcm is equal to r. Now xcm, so r is equal to, so m1 x1 plus m2 x2 by m1 plus m2, like that. So m1 is small m multiplied by r by 2 plus m2 is 3m multiplied by x divided by 4m. So that means we have to find out x, right? So 4r is equal to r by 2 plus 3x, implies 3x is equal to 7r by 2. So x is equal to, implies so x is equal to 7r by 6. This is the answer. So in place of r you can substitute the value. R is equal to how much? U square by g sine 2 theta, where for u you have to substitute 100, for theta you have to substitute 37 degree. So in fact here finding out this velocity as v naught 4 by 3 u cos theta, this is not needed at all. In this problem it is not needed. That is a different approach, you can do it that way. But if this is the easier way to do the thing, that that trajectory of the center of mass would be same as if nothing has happened. Now this m is here, 3m is here, center of mass is here. So you can simply apply the formula of center of mass here. So in the second problem, a man of mass m1 is standing on a platform of mass m2 kept on smooth horizontal surface. That means there is no friction between ground and the plank. So this is the plank of mass m2, man of mass m1. Now find the recoil velocity of the platform if he starts moving on the platform with velocity v0 relative to the plank. So I have a habit of considering all the displacements and velocities towards the right. So in that way, it's my preference. You can have your own preferences, say. So I'll do this. So let the velocity of the platform be v towards the right. So I know it will come out to be negative because of the simple fact that the man pushes the plank this way with a friction force. There is friction between the man legs and this plank. So in that case, friction is applied on the man too in the forward direction. So plank will move towards left, obviously. But if I consider it towards the right, then I'll get a negative answer. And knowing that I'll get a negative answer, still I assume that v is towards the right. Now, so here as there is no external force, so conserve momentum. There is no external force along horizontal, conserve momentum. So initial momentum is equal to final momentum. So initial momentum is 0 as all the particles, the plank and the man was at rest. So final momentum for the plank it is m2v, for the man it is m1 into v0 plus v, because it is given that man starts moving on platform with velocity v0 relative to the platform, and that too is given towards the right. See, to the right. So simple. So that will be added, right? So this is actually the velocity of man with respect to ground, or with respect to ground frame rather. So now, so you have to find out v. So v is equal to minus m1 v, right? Minus m1 v naught divided by m1 plus m2. So that implies the plank moves to the left with a speed of this m1 v naught by m1 plus m2. So as the plank moves towards the left, that is why it is known as recoil velocity. See, here it is given A and B, each of mass m, stand on two ends of a boat of mass capital M at rest. All were at rest before. So B jumps with a velocity v naught. B will jump on water, right? Not on the boat. So B is clever enough to jump to the right. Find the velocity of boat after B jumps. So while B jumps, A is already there, and given B jumps with velocity v naught relative to final velocity of the boat. So this is the situation we are dealing with. This is the boat. Now so at start both were at rest, and finally say v1, say v1 be v1 equal to velocity of boat with A, actually with A, right? So A doesn't get down from the boat, right? With A after B jumps off the boat, right? So we can conserve momentum here in the horizontal direction, starting both are all are 0, right? Velocity of A, B and the boat were 0. Now finally A plus boat, see, M plus small m plus capital M into v1 plus small m. Now it is given B jumps with a velocity v naught. B jumps with a velocity v naught relative to final velocity of the boat. So velocity of B is actually v naught plus v1. So here what you get is 0 is equal to m v1 plus capital M v1 plus m v naught plus capital M v1 implies, so we have to find v1 here, right? So v1 multiplied by 2m plus capital M is equal to minus m v naught, implies v1 is equal to minus m v naught by 2m plus capital M. So this has a minus sign because the boat moves towards the left. So this is answer to this part A of the question. Find velocity of boat after B jumps. This is the answer. Now next part of the question is there. Now A jumps with velocity A jumps with velocity v naught relative to the boat. Now here let v2 be final velocity of the boat, after A jumps off. So A has to jump off, so he's clever, so he'll jump towards the left. So now the initial situation is this: m and m both are traveling with velocity v1. v1 in forward, that means actually it is traveling towards negative direction, because v1 itself is negative, but we will consider everything towards right. Now see, this is what, so this a, so that is a, so a jumps with a velocity v naught towards the left, relative velocity, so that is v2, v2 final velocity of the boat. So by relative velocity, velocity of a is velocity of a relative to boat plus velocity of the boat. Now I'll draw the vectors. Velocity of the boat, final velocity of the boat is v2, this one this way. Now velocity of a relative to the boat is v naught. So let's take this positive direction, this has positive direction. So actually va with respect to boat is v naught here towards the left, and v boat is v2. So we can write with signs, not with vector symbols. So v a with respect to boat, as per the x-axis sign convention, v a with respect to boat is minus v naught, and v boat is plus v2. Therefore va is equal to v2 minus v naught. Okay, so the final velocity of a is, final velocity of a, we'll consider all the velocities towards the right, that's why final velocity of a is there, v2 minus v naught, right? So this is a relative velocity actually, this v naught is a relative velocity. So again we can conserve momentum for this case. So what will it be? Small m plus capital M times v1 is equal to small m times v2 minus v naught plus capital M times v2, implies to find v2, right? So small m plus capital M times v1 plus small m v naught is equal to small m plus capital M times v2. Now if you name this as equation 1 and name this final as equation 2, from equation 1 put the value of v1. So after substituting v1, so basic thing I wanted to explain is the sign conventions. So you have to choose any positive direction, right? That is the easier way to solve this type of problems. Here blocks A and B have mass m each. Now both are having mass m. Now some velocity is being supplied to block A. Starting, so at start both were at rest. See, it's written system was at rest with spring at its natural length. Now A is imparted a velocity v naught, this one v naught towards the right by a sudden impulse, or impulsive force rather, by a sudden impulse. That means you knock it suddenly by a stick and provide it a velocity v naught towards the right. Find maximum compression in the spring during the motion. Now maximum compression, so when the length of the spring is minimum or maximum. So this is the length of the spring L. So I'll neglect the size of the block, suppose. So we have to neglect the size of the blocks to understand it, make it simple. See, so these are the blocks, and this is the length of the spring L. So the length of the spring varies, right? So this is the coordinate x1 of block 1 and the coordinate x2 of block 2. So we can write that length of spring at any time t, as the length varies, is equal to x2 minus x1. So L is equal to x2 minus x1. So if L is minimum or maximum, you know dl by dt is equal to 0. By maxima and minima we know that. So you know dl by dt is dx2 by dt minus dx1 by dt. So dx2 by dt is v2, dx1 by dt is v1. So this is v1 velocity of block 1, v2 velocity of 2. Now when dl dt is minimum or maximum, this term is equal to 0. So implies v2 is equal to v1. So while the spring length is minimum or maximum, the velocities are equal. Okay. So we can proceed to solve the problem in such a way. So this is the initial state which is drawn. I'll draw it again. The initial state and the final state, just I'll draw side by side. So initial state, spring is at its natural length, this speed v0, this has speed 0, and final state, the spring maximum compression, right? So maximum compression equal to x in the spring. Suppose the maximum compression in the spring is equal to x, then the speeds are v each, then v is speed of each. Each of A and B. So we can conserve momentum. By conserving momentum of the system, because there is no external force. Once the impulse is given, it's removed, the stick is removed, it is no longer there. So it's mv0 is equal to mv plus mv, final momentum of the system, implies v is equal to v0 by 2. So final velocity of both the blocks A and B is equal to v0 by 2. Now we will apply the work energy principle. So let x be maximum compression, x equal to maximum compression in the spring. Let x be maximum compression in the spring. So now we will write the work energy equation. So at start, what is the kinetic energy? Half mv0 square. Final kinetic energy is half mv square for each, so it's multiplied by 2, plus half kx square potential energy stored in the spring. So therefore we get half mv0 square minus m into v square. So v is v0 by 2 square is equal to half kx square, implies half kx square is equal to half mv. So mv0 square, half minus 1/4, that becomes 1/4 only. So there you have 2. So therefore x is equal to v0 root over of m by 2k. So this is the answer This is the maximum compression in the spring. In this problem it is different. Instead of giving a velocity, here an external force F naught is applied on block B, while at start both the blocks and the spring also were at rest, springward at its natural length. So now how do you conserve momentum here? So it's not possible to conserve momentum, and it won't be conserved also because there is external force on the system. Now there is a principle from the center of mass frame, from CM frame of any system. What happens? CM frame of any system, suppose there is a system of several masses m1, m2, m3 having accelerations, say a1, a2, a3, like that. Okay, some CM frame of any system, suppose this is a system. So what is the net force on the system? Net force on the system. So net force on the system is, so m1 into a1 minus ACM plus m2 into a2 minus ACM, because it is from the CM frame. So acceleration of particles, say acceleration of any particle p with respect to CM is what? Acceleration of p with respect to CM, that is acceleration of p minus acceleration of CM with vector signs. So this is how it goes. So plus m3 into a3 minus ACM, like so. So what is the final result of this? So what will you get? Net force on the system as, so net force on the system is, so it happens to be m1 a1 plus m2 a2 plus m3 a3, like that, minus the total mass of the system, right? m1 plus m2 plus m3 plus this multiplied by ACM. So by definition of center of mass, this is 0. So therefore the conclusion is that, from CM frame the net force on the system is equal to 0. I mean including the pseudo forces, remember that. So including the pseudo forces. So from there on we can start working. So what we'll do here is now that we'll work from the CM frame. For this problem we will work from the CM, or for the problems of this type we'll work from the CM frame, because from the CM frame the net force on the system is 0. So as you see in this system, I'll work out a bit here. So for this system, what is the force? So this is the blocks, the force is F naught. So this block A plus block B is a system, right? So the horizontal force is F naught. So we can write F naught is equal to total mass into ACM. So implies ACM equal to F naught by 2m. So that is actually acceleration of center of mass of the system. Now we will observe from center of mass of the system, because we will solve the problem from CM frame. Why solve from CM frame? Because from CM frame the net external force is 0, so we can conserve momentum from CM frame, remember that. So from CM frame, so I'll do it here. This is a CM. From CM frame there will be pseudo forces. How much is the pseudo force? So that is M times ACM towards the left. See, because CM is accelerating towards the right, so this F naught by 2M is towards the right. Now this is 2M multiplied by ACM. Apart from there, so apart from this you have the external force F naught also. So M into ACM becomes how much? F naught by 2. So 2M into ACM becomes sorry, that will be 3M, right? I have made a mistake. If not, so 3M. So total mass is 3M. I forgot that. 3M. So 3M here. Not 2M. Forget it, right? It's 3M because the total mass is M plus 2M. I missed out that. Okay. So that's not F naught by 2. That is F naught by 3 rather, right? There it is, F naught by 3, and 2M, it is 2 F naught by 3. So now we can draw actually the net force. So if I draw like this, the net force on A towards the left is F naught by 3, and on B towards the right also it is F naught by 3, and that is from the center of mass frame. Now this will the spring find maximum extension in the spring, right? So see, this is the system. Again I am drawing the diagram, F naught by 3, F naught by 3. Now maximum extension, so A goes this distance, block A goes this distance, and block B goes this much distance, right? So suppose this goes a distance XA and block B goes a distance XB, all from center of mass frame. Remember that it is all happening from the center of mass frame. So now we can apply work energy theorem here. Work done by, see, it starts from rest, right? It starts from rest, and as it is maximum length, so both will end up at rest from CM frame, because also from CM frame, remember, also from CM frame, so any system has momentum 0, right? This work is up to you. You can try and find out the reason why. You can try and prove it why. So from CM frame the net force is 0 and the net momentum of the system is also 0. So both will be at rest. So it's like us stretching two blocks joined by a spring, starts from rest, and at the extreme it will end up at rest. So XA and XB are the displacements of A and B. So the maximum extension is equal to XA plus XB. Okay. So let's work out on it. So F naught by 3 multiplied by XA, work done by this force, and again plus it will be work done by this force multiplied by XB. So plus F naught by 3 multiplied by XB equal to the no change in kinetic energy, so change in potential energy, so half K into XA plus XB square. So that means, that implies F naught by 3 times XA plus XB is equal to half K xa plus xb square implies xa plus xb is equal to 2 f naught by 3k. This is, we have found the maximum extension in the spring. So rod of length L slides between wall and floor with velocity v naught. So with the end B having velocity v naught. Find velocity of center of mass, that is the midpoint. Find velocity midpoint of the rod. So here we can find out velocity of the end A. We know already the method. So A will obviously move downwards, slide along the wall. So that is, say, VA. Okay. So now what we do here? So with respect to A, B will be, that relative motion is circular motion. So with respect to A, B will move in a direction perpendicular to it, perpendicular to the length. So that is, this is vector VB. Now you have to subtract VB minus VA, right? So minus VA. Here I am using triangle law. You can use parallelogram law or anything. So this is vector minus VA. Triangle law is simple, just join tail to tail, that it works. So A as the reference. So A, with respect to A, this will be actually velocity of B relative to A. Okay. Now what about the angle? So this angle is theta. So this angle is 90. So this is 90 minus theta, right? So again this angle is theta. Okay. Now magnitude of this velocity is v naught and magnitude of this velocity is va. So v naught divided by va is equal to tan theta. Simple geometry of the right angle triangle. V naught, so this side divided by this side is tan of theta. So that means VA is equal to V naught cot theta. Okay. Now we'll quickly find out velocity of the midpoint C. So position vector of the midpoint. So coordinates, say XA, suppose this is a point, midpoint formula. If you know midpoint formula, so suppose this is point A and point B and C is the midpoint. Okay. So and see, this is having coordinates XA, YA, and this is having coordinates XC, YC, and B is having coordinates XB and YB. So XC is equal to half of XA plus XB, and same holds for Y also. YC equal to half of YA plus YB. So if you combine these two, you can write position vector. So RC is equal to half of RA plus RB, right? Because simply R is equal to R is xi cap plus yj cap. So this follows actually from there, right? So as this is true and this is true, multiply this one by I cap, and multiply this whole thing by j cap, right? You get this. So xc I cap is equal to half of xa I cap plus xb I cap. Similarly, yc j cap is equal to half of ya j cap plus yb j cap. So now you just add these two. Just you add these two expressions, you will get. So xcy cap, so xci cap plus ycj cap is what? rc. Same way, so you get rc is equal to half of ra plus rb. This is a midpoint formula with respect to position vector. So if you differentiate this, then what you get? ddt of rc is half ddt of ra plus ddt of rb. Position vector, after you differentiate, you get velocity vector. So vc is equal to half of va plus vb. So in that way, if you consider the x-axis there and the y-axis there, then velocity of b, what is velocity of b, is v naught times I cap. Now velocity of a is minus v naught cot theta times j cap. Therefore velocity of c is half of minus v cot theta times j cap plus v naught I cap, this way. So you can find out the magnitude, but this is in vector form, velocity of the midpoint c. So here wedge of mass m rests on smooth floor, ball of mass small m released from the position shown. So the system was at rest. Find the speed of the wedge when the ball reaches bottom. So see, if you see, the slope of the wedge is the wedge, the surface of the wedge is parallel to ground almost as it touches ground. So finally the ball will move horizontally. So I'll draw the final position here. The initial state of the system is already drawn. So there is the ball. So you have to find out what? Velocity of the wedge. So let velocity of the ball be v1, velocity of the wedge. This time I am taking it towards negative direction of x. Sorry. So you can take it towards positive and expect for a negative answer for v2. That also works. So here, this between this state and this state, we conserve momentum along horizontal, right? Along vertical, it's not conserved, because vertical you have gravity, but there is no horizontal net force. Horizontal net external force is absent. Conserve momentum along horizontal, or if you name an x-axis here, that's fine. So initial momentum equal to final momentum. Initial momentum equal to final momentum, all along x-axis or horizontal direction. So initially all were at rest, so 0. Final momentum m into v1 plus m into minus of v2. v2 is a magnitude, but it is chosen towards negative direction. So I can write finally mv1 equal to capital M times v2. Let's name this equation 1. Next equation you will get from work energy. So the loss in potential energy is gain in kinetic energy, and that too for a system, for the whole system, not for individuals. So the loss in potential energy is mgh, and gain in kinetic energy is half m v1 square plus half m v2 square. So this is equation 2. So from 1 and 2 now we will solve for v2. So we can substitute v1 from equation 1. Substitute v1 is equal to mv2 by small m. So here I will write mgh is equal to half m capital M square by small m square times v2 square plus m by 2 v2 square implies, can write here, so this m square and m, this will cancel. So there you have m, or rather 2m, and in numerator you have m square plus small m into capital M. This whole thing multiplied by v2 square implies v2 is just multiply this 2m square gh divided by m square plus small m into m. This problem is slightly different from question number 7. It has been asked that find velocity of the wedge when block reaches its bottom end. Okay. So here, as in the last problem, the surface of the wedge is not flat near ground. So it makes angle theta with horizontal. So we'll draw the final position here in the diagram. It was all released from rest. So this is the final position. So and the block is here. Okay. And say final velocity of the wedge be v2 and final velocity of the block be v1 relative to the wedge. Remember that it's not, and see v1 is not absolute velocity, it is relative velocity. So final velocity of wedge is v2 to the left, and final velocity of block is v1 with respect to wedge as in figure. So what is the absolute velocity? So velocity of block relative to wedge is velocity of block minus velocity of wedge. So what is velocity of block relative to ground? That is velocity of block relative to wedge plus velocity of the wedge. So velocity of block relative to wedge is this one, and velocity of the wedge is this one. So I'll draw it here again, velocity of the wedge, for the sake of adding this one, v2. I'll put the star mark here. So so the combination or vector sum of this and this will give you the velocity of the block relative to ground. So let's split it into x and y components. So that's the x-axis and that's the y-axis. So if you split this into components, you have, as this is theta, so v1 cos theta, and that is v1 sin theta. So what we can do here is that, so we can draw the final velocity vectors. again I am drawing this final velocity vectors. Now with respect to all this x and y components I'll draw. So this has velocity towards x-axis v1 cos theta minus v2, and downwards it has v1 sin theta. And what will be the resultant velocity here? Resultant is actually root over of, just you square and add those, you get v1 square plus v2 square minus 2 v1 v2 cos theta. If you square and add those, you get this only. And also this is the formula of vector addition, if you remember. Two vectors at an angle 180 minus theta, so that is v2 here. So we can conserve momentum along x-axis. Conserve momentum along x-axis because there is no net external force in the x-axis. So small m times v1 cos theta minus v2 is equal to capital M times v2. This is one equation. Next equation is work energy. From work energy, so the loss in potential energy is gain in kinetic energy. Loss in potential energy is mgh, and gain in kinetic energy is half m v1 square. That means I'll square up this thing, resultant velocity, and then I'll square up this v2. So v1 square plus v2 square minus 2 v1 v2 cos theta plus half capital M times v2 square. Okay, so you have to solve for v2, so you have to substitute v1. So let's name this equation 1 and equation 2. Now from equation 1 v1 is equal to m plus capital M v2 divided by m cos theta. Now this you put in equation 2, and then the final result you get is, after solving equations 1 and 2, this is the final result you get.